So here we're going to look at the second application problem that involves differentiating trig functions, and this is taken from the 2012 HSE towards the back end of the paper. And again, this is a good question because it involves differentiating trig functions, but the actual principles around this question bring in a lot of the linear functions and a lot of the work around things like equation of a line, gradient, and some area as well. So it incorporates a lot of different topics mixed together. But it does require you to differentiate a trig function. So this is the typical type of question you'll get at the end of a HSC paper where you're asked to bring lots of various areas of the course together and apply your knowledge from lots of different areas of the course together in one question. So we're going to try and break this down as best as we can. Before you have a look at this, we'll just have a quick read through. It says the diagram shows a point T on the unit circle x squared plus y squared equals 1 at an angle theta from the positive x-axis where theta is between 0 and pi on 2. Which tells us it's just in the first quadrant, which makes sense, imagining that our axis are the quadrants and our semicircle exists just in this first quadrant here. So therefore our angle is between 0 and pi on 2. It says the tangent to the circle at T is perpendicular to OT and intersects the x-axis at P, and a line y equals 1 intersects the y-axis at B. So there's a lot of information here. It's always good sometimes just to have a look at this and see if we can write down any further information from this particular question. Now, start with that. Do we know the coordinates of any of these? Any here? Do we know any of the values? We know this is a unit circle, so therefore the radius is 1. So therefore this length here is 1. We also know that this height here is 1 as well. And we can write down some coordinates here. So B therefore has coordinates 0, 1. P, we're not sure the coordinates of P except that the y coordinate is 0. Q, we know that we don't know its x coordinate, but we do know that its y coordinate is 1 because it passes through the line y equals 1. We do actually know the coordinates of T because this lies on the unit circle. T has coordinates cos theta, sine theta by definition of a unit circle. And just as a bit of a recap on there, in terms of where they come from, let's say that this is, we'll turn this into a right angle triangle. We'll say that this is our x value and this is our y value. And in terms of our coordinates for T, is the distance along here is our x coordinate, the distance from there to there is our y coordinate. Well, just as a reminder, using the trig functions, let's say we take cos theta, which is adjacent over hypotenuse. So cos theta is equal to adjacent, which in this case will be x, over the hypotenuse, which is 1. So therefore x over 1 is just x, and we end up with x equals cos theta. We also then do the same thing for y, and we get y equals sine theta, hence how we can write our coordinates of T as as cos theta sine theta. Now, I think that's most of the information we can get down from this. So what we're going to do is we're going to start with part 1, which says show that the equation of the line PT is x cos theta plus y sine theta equals 1. So equation of a line, we start to generate some ideas here around what equation of a line means and where we've heard that before and what we know about it. And the main thing that probably springs to mind is the equation y minus y1 equals mx minus x1, which is the equation of a straight line. 2 bits of information are needed for this though. We need a point that the line passes through, which is x1, y1. We also need the gradient of the line, which is m. Now, we actually know a point that this line passes through. We can see that PT passes through P and it passes through T. Now, we don't actually know the full coordinates of P, but we do know the coordinates of T. So we can say the line passes through T, so we've got our x1, y1, but we need the gradient. Now, we need to look at this and work out how we can find the gradient of PT. The one bit of information we've got about PT is the fact that it is perpendicular to OT. Now, perpendicular, when we start to see the word perpendicular, we can think of gradients and two lines that are perpendicular to each other. When you multiply together their gradients, you end up with -1. So therefore, the gradient of PT times by the gradient of, sorry, that was just my pen, gradient of OT. So when you multiply those two together, those two gradients, we'll end up with -1. Now, we can find the gradient of OT, this line here, because the gradient of any straight line is simply tan theta with the positive angle that it makes to the x-axis. So therefore, we say the gradient of PT, times by tan of theta is equal to -1, and therefore the gradient of PT equals -1 on tan theta. So we've got the two bits of information that we require. We've got the gradient of the line of PT, which is -1 over tan theta, and we've also got our point. So we've got the point, which is cos theta sine theta, and we've got the gradient, which is equal to -1 on tan theta. So therefore, we can use our point gradient formula, y minus y1, y minus tan theta, equals the gradient, -1 on tan theta, x minus cos theta. Alright, now, rather than expanding this out, this makes it a bit easier. We're going to multiply through by tan theta, firstly, so we end up with, in fact, looking at this, if we multiply through by tan theta, we're going to end up with a lot of tan thetas in our expression, and given that it's a show that question, always have a look at the answer. Notice there's no tans there, it's just cos theta and sine theta. So let's see if we can implement that into our solution. I'm just going to make this a bit smaller, just so I'm not going to run out of room. So how we can do this, we know that tan theta equals sine theta over cos theta. So we actually know that 1 on tan, which is the same as cot theta, equals cos theta on sine theta. So what we can say is, well, therefore, actually, y minus sine theta is equal to negative cos theta on sine theta, x minus cos theta. All right, now we can simplify this. Let's multiply through by sine theta. And what that's going to leave us with, it's going to leave us with y sine theta minus sine squared theta equals negative cos theta times x. I'm just going to put the x in brackets so it doesn't confuse us. Now we've got negative cos theta times negative cos theta, so plus cos squared theta. Right, well, this is starting to look a little bit like what we had before. Just to relate that back, we're looking for x cos theta plus y and sine theta. So let's bring the x cos theta over, and because I wrote the x in brackets, remember we can just write that at the front. So we end up with y sine theta plus x cos theta. Now we've got this minus sine squared theta on the left hand side, and we've got cos squared theta on the right hand side. I'm going to move the sine squared theta over, so we're going to move cos squared theta plus sine squared theta. And for those of you with a good memory regarding the trig identities, we know that cos squared theta plus sine squared theta is 1. So therefore, y sine theta plus x cos theta equals 1, which is exactly what our question is asking us for. Now, part 2 is, I just round up part 1. Really, if you think of it, there's no calculus involved with that. Part 1 is purely using the equation of a line, information about the gradient, information about point gradient formula, and then some trig identity knowledge. So all that is really prelim content. There's nothing there complex, but it is asking you in a funny way. It's not asking you to do that directly. And the challenge here and why this is a bit more difficult is because you have to make those connections yourself. Now, part 2 is asking us to find the length of BQ in terms of theta. So BQ, let's just identify this in our diagram. BQ is this length here. Okay, now, if we look at the length of that is actually just the x-coordinate of Q. So it's this value here, which we'll call x1. Now, we don't know what that is at the minute, but we do know that Q passes through our line PT. And if we can find the x-coordinate of Q, that will actually tell us the length of that line. So let's, what we've got to now think about is how can we use these earlier parts of the problem to help us out with these later parts. So part 2 has to find the length of BQ. Basically, we want the x-coordinate. Well, we know what the y-coordinate is, and we know what the equation of the line PT is that it passes through. So we can use all of that to help us find that x-coordinate. So from part A, from part 1, we've got that y sine theta plus x cos theta equals 1. Now, let Q be the point x1, y, and the distance of BQ is equal to the value of x1. Now let's sub these values into, Q is not the value x1, y, my mistake, sorry, it's x1, 1, okay? Let's sub these values into our equation. So y sine theta plus x cos theta equals 1. We end up with, well, y is 1, so we end up with sine theta plus x1 cos theta equals 1. We want to rearrange this and solve for x1, so we take sine theta across the other side, so x1 cos theta equals 1 minus sine theta, and therefore x1 equals 1 minus sine theta on cos theta. Notice in the question it does say find it in terms of theta, and you'll find again with these questions later on in HSC, it's very rare with these earlier parts that you actually get whole numerical answers. A lot of it is building towards using these values and expressions or terms later on to help solve a bigger problem. So that's find the length of BQ in terms of theta, and just a reminder that we found the x-coordinate of Q. So Q actually has coordinates, if we just write those down, of x-coordinate 1 minus sine theta on cos theta, with a y-coordinate of 1. Now, moving on from there, part 3, show that the area of the trapezium OPQB is given by A equals 2 minus sine theta to cos theta. So, trapezium OPQB, let's mark that out, OPQB. So that's this trapezium. Start to see maybe where this length BQ is going to come into play here. So, firstly we want to find the area of this trapezium. So we need the area formula for a trapezium. So part 3. And that is the area of a trapezium is equal to the two parallel sides, A plus B, times by the perpendicular height between them, times by a half. So let's have a look at the two perpendicular sides. Well, the two perpendicular sides are here. That's going to be A, that's going to be B, and this side here is just the height. So we've actually got two of those values. We've got H, we've got A. We need to find B, so we need to find the length OP. Now we can formally write this down first of all. Is that the area is equal to a half A plus B. Well, A is the length, if we directed it as BO, plus OP times by the height, which is O to B. So one sec, sorry, that's BQ. That'd be O. So the area of our trapezium is the two parallel sides, so these two added together, BQ plus OP, times by the height between them, times by BO, times by a half, or divided by 2, depending on how you want to look at it. And from there, we can then substitute in some of these values that we know. Well, let's start off half, that's fine. BQ, the length BQ we worked out in the previous part of the question, that's 1 minus sine theta on cos theta, plus OP, we don't know OP at the minute, times by beta O. Well, beta O is just the length 1, which we see in our diagram there. Beta O is just this length here for beta O. Now, we need to find the length here of OP. Now, similar really to what we did in the earlier part, in part 2, we want to find that that's just the x-coordinate of P. Well, again, we know the y-coordinate of P is 0. So what we need to do here is we need to find the length OP first of all. So to find length OP. So using part 1, just a reminder that is y sine theta plus x cos theta equals 1. P has coordinates. Now we'll say its x coordinate is x2, its y coordinate is 0. So we go ahead and sub this in. So we've got 0 sine theta plus x cos theta equals 1. Sorry, x2 cos theta equals 1. 0 times sine theta, which is 0. So we do x2 cos theta equals 1, and therefore x2 equals 1 on cos theta. So therefore OP is equal to 1 on cos theta, and therefore the area is equal to a half 1 minus sine theta on cos theta plus 1 on cos theta. Now these two fractions in the bracket actually have the same denominator, so 1 minus sine theta plus 1 becomes 2 minus sine theta if we add the two ones together, all over cos theta, and then if we times through by the half, we end up with 2 minus sine theta on 2 cos theta, which I believe is what the question is asking for. So that is part 3. Now part 4 is then bringing all this together. Find the angle theta that gives the minimum area of the trapezium. So let's have a look at minimum. As soon as we start to see minimum, we start to think differential, we start to think stationary points. And what we're minimizing is theta, so that means we're differentiating with respect to theta. So this is the area, so minimum area, so we're differentiating the area with respect to the angle. So we're doing dA on d theta. So where that's going to come in now is in this next part, given that in that part 3, we were just to find the function for the area in terms of theta. In part 4, we're now going to be asked to differentiate this in terms of theta. So we've got the area equals 2 minus sine theta over 2 cos theta. Again, quite common towards in the HSC questions, these maximisation, minimisation questions. They'll give you the function. It might be that you can't actually answer part 3, but you still know what the function is because it's a show that question, and you can use that then in the next part of your answer to help you with part 4. So what we're going to ask to find is we're going to ask to find the minimum area, or the value of theta gives us the minimum area. So what we need to do here is we need to differentiate, and we can see that this is a quotient. So we've got u equals 2 minus sine theta, and we've got v that equals 2 cos theta. So we need to go ahead and differentiate these. U dash minus sine differentiates to minus cos, and the 2 differentiate is a constant, so it ends up being 0. V dash 2 cos theta differentiates to minus 2 sine theta, because cos differentiates to minus sine. And v squared will be 4 cos squared theta. Now, when we go ahead and use the quotient rule here, we have u dash v, so u dash times v, so negative cos theta times by 2 cos theta. That becomes, so if we get dA on d theta, negative cos theta times 2 cos theta is negative 2 cos squared theta, minus 2 minus sine theta times negative 2 sine theta. I'm going to just write this in a bracket to avoid making some simple multiplication errors. All over v squared, so 4 cos squared theta. Now, from here, what we can do is we can do quite a bit of simplification. We need to expand this bracket first of all, so negative 2 cos squared theta minus, well, let's expand this out. So 2 times negative 2 sine theta is negative 4 sine squared theta. Minus sine theta, sorry, take that back, it's not that at all, because it's times 2 by it. Sorry, 2 times negative 2 sine theta is negative 4 sine theta, And then minus sine theta times by negative 2 sine theta is plus 2 sine squared theta. And now we can finally write all this out here. So what we end up with now is negative 2, sorry, that's all over v squared v 4 squared theta. Negative 2 cos squared theta. Negative times a negative 4 sine squared theta is plus 4 sine theta. Negative times 2 sine squared theta is negative 2 sine squared theta. All over 4 cos squared theta. And again, we can just rearrange this. Now notice we've got a cos squared theta and a sine squared theta. Both got negative 2 out the front. I'm going to just write that as minus 2 cos squared theta minus 2 sine squared theta plus 4 sine theta over 4 cos squared theta. And now you can notice we can take negative 2 out as a common factor, negative 2 lots of cos squared theta plus sine squared theta plus 4 sine theta all over 4 cos squared theta. And we can actually go ahead and we can simplify this because cos squared theta plus sine squared theta is 1. So we end up with negative 2 plus 4 sine theta. So that becomes negative 2 plus 4 sine theta all over 4 cos squared theta. And each of those terms divide by 2. So we end up with negative 1 plus 2 sine theta over 2 cos squared theta as our derivative. Now, again, that's just differentiating it. We're being asked to minimize the value of theta, or minimize the area and find the value of theta that will give us a minimum area. So what that means is we need to solve dA on d theta equals 0. So that is minus 1 plus 2 sine theta on 2 cos squared theta equals 0 times 2 cos squared theta across the other side. So we just ended up actually solving minus 1 plus 2 sine theta equals 0. And if we rearrange that, we end up with sine theta equals half. Now, just a reminder, theta is only in the first quadrant, and therefore we only need one value of this, and that is theta equals pi on 6. However, we need to test this particular value. Last thing, we need to show it provides a minimum. So we don't have the second derivative, and finding the second derivative, this will be quite complicated. So we're going to use the table test for this. So theta and dA on d theta. So pi on 6, value bigger than pi on 6 is pi on 3, value smaller than pi on 6 is pi on 8. And pi on 6 gives us a gradient of 0. Pi on 3 gives us a value of 1.46, and pi on 8 gives us a value of negative 0.137. So we just sub those values of theta into the derivative, so into this here. Now, that's negative, so it has a negative gradient. 0 has a horizontal gradient. Positive has a positive gradient. Therefore, we can see that theta equals pi on 6 gives the minimum value of the area of the trapezium. Now, there's a lot of work has gone into that. Notice though, that's a question you're going to get towards the end of the paper. So there's lots of bits and pieces going on. Just to remind, we started off, first of all, adding extra information to the diagram. Do we know any more information about the coordinates? We have to find the equation of the line, which just used the point gradient formula with a gradient and a point it passes through. We have to find the lengths of some functions, which involves some rearranging. We have to find the area of the trapezium. Now, a lot of these questions you're going to look at, and the answer won't come to you clearly or straight away. But what you're required to do is just write a few of these ideas down, start relating it back to what we're going to call simple maths. And in terms of area of a trapezium, you know how to find the area of a trapezium. So start by writing out, well, what values do you need to find the area of a trapezium? Do you have any of those values? If you do, great, sub them in, use them. If you don't, can you find them? Can you then obtain them and then sub them in and include them as part of your expression before simplifying? A reminder that all show that questions always have the answer provided in the question, and you can always refer back to that and look as if though you are going along the right lines, and for some hints as well, maybe about some substitutions that you need to use, some simplifications that you need to use. And then the very last part of the question was find the angle theta that gives the minimum area of the trapezium. A few keywords there that highlight to us that this is a maximization problem or minimization problem, and we need to find the derivative. We know that we're using the part 3 there because it's talking about the minimum area of the trapezium, which is what we found the formula for in part 3. We go and this is where the only trig calculus is involved in this question is part 4. We go through, use the quotient rule to differentiate it, and then to solve for the first derivative is equal to 0, because we're looking for a minimum value, so we need to solve for dA and d theta equals to 0. And then the very last piece of the puzzle is we just have to test that value to show that it gives the minimum value of the area of the trapezium. So there's a lot going on there, but a lot of stuff that you can really get good marks on, because the difficulty with this is not the actual maths itself, it's more about relating the different areas together and recognising, being able to recall those different bits of the course that we've covered to help you answer the question and bring all those bits together.